which is the beginning of Chapter 1 in the Fluid Dynamics, Fluid Mechanics textbook. I will be covering sections 1.1 through 1.3 in this particular chapter today, and then I will work 2 problems and assign the homework problems, or I've already posted the homework assignment up to our website. If you look at the website, here we've done the introductory material. The material for exam number 1, you'll see that I've posted a file called Homework for Chapter 1, and that the homework problems are there. Up through at least 12 are the problems that you could do for tonight before you watch Vodcast number 3. So, continuing with that, let's talk a little bit about Chapter 1, sections 1, 2, and 3. If you look in your textbooks, we're really starting on page 3 and continuing through to page 12. And there's really not much on section 1.3. It's just a very short 2 paragraphs that talk about what we're doing. But let's talk a little bit now about fluids. So I'm going to go to the document cam and get started. All right. So first of all, when we talk about fluids, we're talking about substances with particular characteristics. Okay, lights shifted a little bit in here. All right. What is a fluid? Okay. First of all, we're used to thinking about fluids as just being liquids, but fluids are actually liquids, gases, plasmas, combinations, and a lot of different things. In general, we know that a fluid does not necessarily respond very well to certain kinds of force. Particularly, if you take a solid of any sort, if you have a block, a cube of ice, for example, if you push on it in this manner, perpendicular to the surfaces, that's referred to as a normal force, or it creates a normal stress. If you push on it parallel to the surface, that is referred to as a shearing force or a shearing stress. And in general, fluids do not respond to shearing force. The only type of stress that a fluid can bear normal stresses only. And depending on the nature of the fluid, what happens if you subject it to a shearing stress? Well, if you take a cup of water and you pour it out onto the surface of a table, what basically happens is the fluid shears against itself and it does not maintain its shape. So instead of bearing the shearing stress, it just collapses and does not bear that stress at all. If you push on a fluid, on the other hand, if you have, for example, this cup, and you fit the cup with a piston, and you push down on it with some sort of a normal force, what will happen is that if fluid is completely incompressible, it will just push back. And if it is slightly compressible, it will get a little bit smaller. And if it's very compressible, it will get smaller still. So you will have an increase in pressure, a decrease in size, based on the type of a normal force that you press upon it. Now, this is also true for large amounts of fluids. For example, if you think about a dam, and if this is a side view of a dam, and if you have a water level behind the dam, what you find is that the pressure at increasing depths increases because of the weight of the water above it. If water pushes against the dam perpendicular to the face of the dam, the water can stay in a hydrostatic configuration with the dam. However, if the water moves in this type of a fashion, the fluid won't bear any shearing stress, and so the fluid will just move. So a shearing stress creates movement in a fluid, and a normal stress does not. A normal stress will cause a compressibility or an increase in pressure. So the technical definition of a fluid is defined as a substance that deforms continuously when acted on by a shearing stress of any magnitude. Deforms continuously when acted upon by a shearing stress of any magnitude. Okay? So that's the difference between a fluid and a solid when it comes to bearing stresses. Now, there are a lot of different ways that the deformation will occur, and we'll talk about that as we continue. Now, the study of what fluids do when they are subjected to shearing stress is called rheology. So rheology is a field of science. It's a field of pretty much fluid physics. But basically, rheology talks about how the materials behave, and it can be a little bit advanced. You can talk about rheology of common fluids like Newtonian fluids, which we'll discuss later on, but they're not nearly as interesting as non-Newtonian fluids. So when we talk about any type of a fluid, one thing that we need to remember is when we talk about this idea of continuously, okay, fluids behave as a continuum. Now, this is something that we did not have to think about too much when we talked about solids. But in terms of our analysis, continuum, there we go. When we talk about fluids, we often don't have a particular boundary that we're working with. Like if you have water moving in a stream or water moving through a pipe, you sometimes have to define whether you're going to look at a particular element of that fluid or if you're going to look at a particular location that fluid is passing through. And we'll develop some ways of doing that, but we can't really look at it both ways. When we have a solid, or when we have a container full of a fluid for that matter, we have a pretty fixed control volume, and we can define the boundaries pretty well. But fluids, we have to define the boundaries before we can actually do any of the math to decide what's going on. So the next thing that we need to talk about before we get into fluids is the units that fluids are involved in must be dealt with very carefully. And there's a couple of reasons for that. But one reason that we have to deal with the units very, very carefully is because they can be a little bit complicated. The other reason is there's a field of study called dimensional analysis where we can actually learn more about our substances and what are going on with them by looking at the units. So it's important right from the start to begin with an idea called dimensional analysis. And so first we'll define the difference between units and dimensions, and then we'll talk about dimensional analysis. And that's actually the math topic for this vodcast. So going back to the idea of units and dimensions. Okay, what are dimensions? Those are physical properties. Examples of which can be length, mass, time, force. If we were talking about electricity, we could also be talking about electrical current We could talk about luminous intensity. We could talk about potential difference in an electrical circuit. But in terms of mechanics, we are most concerned with length, mass, time, or length, time, and force. And you can express, of course, mass and force in terms of each other, which we'll talk about in just a moment as well. So if dimensions are physical properties, units are amounts of physical properties or quantities used to measure dimensions. So what that means for us is that if physical properties are length, mass, time, and force, the units that we use to measure them might be, if we're talking about the metric system or the SI system, length could be measured in meters, mass could be measured in kilograms, time could be measured in seconds, force could be measured in newtons. And if we were in the US Customary System, which is also called the British Engineering System, or it has some other names, but I prefer, it's not really a system at all. So what it is just sort of what we're used to using. But the SI system is a integrated, homogeneous set of units. The US Customary System is just shorthand for what we're used to using. We also use something called the British Gravitational System, which looks a lot like the US Customary System. But the SI system is the best defined. If we're talking about US customary or British gravitational, length might be measured in feet. Mass is measured in slugs or pounds of mass. Time is still measured in seconds, minutes, hours. Force is measured in pounds of force. Okay, so we're going to talk about secondary units, and some of these you've seen some of these before. So some of this will be a review to you. We're just going to cut it up a little bit differently. Another name for the US Customary System that your book refers to is the English Engineering System. And as I've said, they're not really systems at all, so that's kind of the big surprise on all of this. So let's talk a little bit about dimensional analysis and some of the units that we need to be familiar with. All right, and then we'll do a couple of problems using dimensional analysis. Okay. First of all, the relationship between mass and force is established by Newton's second law of motion. Force is equal to mass times acceleration. In the SI system, if a mass of 1 kilogram is accelerated at gravitational acceleration 9.8 meters per second, it results in a force of 9.8 newtons, which is also to say that 1 kilogram accelerated at an acceleration of 1 meter per second results in a force of 1 newton. Because here we have 1 times 1 times 1, or 1 times 1 equals 1, and 1 times 9.8 equals 9.8, we can say that the SI system of units is consistent. In the US Customary, or British Gravitational, or English Engineering System, we take, if we have a slug, which is consistent, and we accelerate it at the speed of the acceleration of gravity, which is 32.2 feet per second squared, that results in a force of 32.2 pounds of force. Now, the force of gravity is also called the weight. Right? Because whatever a mass weighs is an expression of its response to gravity at that particular location. Okay, so if we look at this continuing, if we take one slug and we accelerate it at 1 feet per second squared, we get a force of 1 pound of force. Now, the strange part comes in the U.S. Customary System because somebody asked a question, how much mass weighs, in other words, responds to gravity, with a force of 1 pound of force. And if you look at this top equation, you can see that it would be 1 over 32.2 slugs. 1 over 32.2 slugs. And so that amount of mass is defined as 1 pound of mass. So what that tells us is that 1 pound of mass, these 3 dots mean therefore, 1 pound of mass weighs 1 pound of force at Earth standard gravity. But it makes the set of units non-consistent. So to simplify your life, if you are using the U.S. Customary System, use mass in slugs. If you don't, your answers will not be consistent. And if you're given mass in pounds of mass, just remember 32.2 pounds of mass is the same amount of mass as 1 slug. Okay? And if you do that, you'll always be fine. All right, so what we're going to do next is something called dimensional analysis, which is just built on this idea. Let's start with an equation that we are familiar with. Once again, force is equal to mass times acceleration. If I look at the dimensions, meaning the physical quantities, I know that mass is in units of mass, or is in dimensions of mass. Acceleration is in dimensions of length per time squared. So that means in order for this equation to be valid, that force must have the dimensions of mass times length divided by time squared. Now, the protocol for writing dimensions is to use square brackets. Here's another example. We know that velocity is equal to distance per time. So we can say if distance is a length, time is time, it means that the dimensions of velocity are length per time. All right, now the important part about this is that every valid equation, whether it's simple like these two or difficult, but every valid equation must have dimensional homogeneity. It means that everything on the right-hand side has to have exactly the same dimensions as everything on the left-hand side. And if it doesn't, then there's something wrong with the equation, and that the equation, in fact, does not work. So let's talk about dimensional homogeneity, or dimensional analysis. And a few of your homework problems are going to involve this idea. So for homework prep, I will start by doing problem 1.1 in your textbook. problem 1.1, which is on page 32, says, determine the dimensions in a force length time system and a mass length time system for the product of mass times velocity. And what is mass times velocity? What is that quantity? Well, because velocity is the vector form of speed, mass times velocity is momentum. The product of force times volume and kinetic energy divided by area. All right. And we're going to do a force length time system, which is like the US Customary System, and a mass length time system, which is like the SI system. Now, obviously, we can go back and forth between force and mass. It's just that the SI system is more native to using kilograms, meters, and seconds, which is mass length and time. And the US Customary System, or any of its other names, is more comfortable using force length and time, such as pounds of force, feet, and seconds. So let's start with the mass length time. All right. And what we're looking for is dimensions. So we'll do mass length time and force length time. Okay? Mass times velocity. Mass is a dimension. Velocity is length per time. So you can write it like this, or if you want to write everything on a single line, ugh, that looks ugly, you can write it as mass times length times time to the negative 1. Okay? So that is mass times velocity in a mass length time system. Let's talk about force times volume. Well, force, if we go back, how do we find force? Force is equal to mass times acceleration, right? So that means that force is equal to mass times length times time squared, or divided by time squared, or times time to the negative 2. So I can substitute this in for force, and I can say force times volume then is mass length time to the negative 2 times volume. Volume is length times width times height, for example. So that's length to the third. So if we have force times volume, we have that times length to the third. Length to the third times length is length to the fourth. So our final answer for that would be mass length to the fourth time to the negative 2. All right. Our last problem, and then we'll just repeat this in the force length time system. But our last problem, here we have kinetic energy. What is kinetic energy? Well, any energy is, if we go back to the SI system, the units of kinetic energy would be joules, which are Newton meters. And since we have a force here, to write that in terms of mass, we need to go back to our force is equal to mass times acceleration and plug in for force right here. So that means that this is in dimensions of Newton is force, meter is length, and then to put it in base dimensions, we can say this is mass times length times time to the negative 2 times length, or kinetic energy is mass length squared time to the minus 2. So kinetic energy per area is going to be length squared. So for kinetic energy, we would have mass length squared times to the minus 2 divided by area, which is length to the minus 2. Those cancel, and we're left with mass times time to the negative 2 for our dimensions. All right, now how do we convert these into a system of force length time? Well, the answer goes back to Newton's second law. We know that force is equal to mass length times time to the minus 2. If I solve this for mass, I could say that force divided by length divided by time to the minus 2, which is time to the minus 2 in the numerator, is equal to mass. So here's my dimensional equivalency. So every time I have mass up here, all I have to do is substitute in that expression. Let me widen this out a little bit. Maybe. Doesn't want to do it. Yeah, that's all I have. Okay. So if I take this expression and substitute it for this expression, pardon me, and substitute it for mass, instead of putting mass here, mass times length per time, I would put force time squared per length times length per time, and lengths cancel out. One of these times cancel out, and I find that in the force length time system that this will be force, and I have a single time left, force times time, right? And you can go ahead and continue that down here. Instead of mass, put in force times squared per length times length time to the minus 1. Let's just write it down here. Time to the 1. So this time cancels this cancels this, and I'm left with force. I guess that's the same one. So there we go, force time. Okay, down here, you can do the same thing. If it just means do it again, more or less. Okay, so you can finish off those problems. All right, last but not least, let's take a look at problem 1.8. All right, in your textbook, if we read problem 1.8, it tells us that the force P that is exerted on a spherical particle as it moves slowly through a liquid is given by this particular equation. Okay, so we're told that P is a force. Let me get something underneath this. All right, and P is equal to 3 pi mu, which is called viscosity, which is a property we'll discuss in a little bit here, times d, which is the particle diameter, times v, which is the particle velocity. So the question says, what are the dimensions of the constant 3 pi? Well, 3 pi should be dimensionless, but let's find out if it is or not. Anytime you have something like 3 pi, it would be very unusual that it has dimensions associated with this, but basically, let's determine what that is. All right, so we know, let's just say, since this is a force, since P is a force, let's see if we can write these in terms of a force length time system. So we have 3 variables, mu, d, and v. V is velocity, dimensions there would be length per time. D is just length, and then we have to think about mu. We have not really dealt with a viscosity. So the answer to that is the property tables. I may be able to pull this up a little bit nicer from the website. Let me put this on the podium PC. Come back here to introductory material and property tables. Okay, that's clearer, isn't it? So if we go down here to viscosity, you'll see that there's 2 different types of viscosity. And we need to know we're talking about either dynamic viscosity or kinematic viscosity. So we need to determine which one of those they are talking about in problem 8. All right. So On the inside front cover of your book, you'll see the symbols where dynamic viscosity is given the symbol mu, and kinematic viscosity is given the symbol nu. So since we're talking about mu, it's safe to assume, and it's accurate to assume, that mu is what we're talking about in pound-seconds per feet squared in the US system, or Newton second per meter squared. Newton is a force, second is time, meter squared is length squared. Newton second meter squared. Oh, I said that. Newton second meter squared. Yep, we got it. All right, so let's see what we have. If we take this constant 3 pi and we multiply this by the dimensions, sorry, I should use the square symbol, of force, time per length squared, times the dimensions for d, which are just length, times the dimensions for v, which are length per time, and see how that relates to force, which are the dimensions of p. We see that we have t canceling against t. We have length squared in the top canceling against length squared in the top. And we have force is equal to force. So we have force on one side is equal to 3 pi times force. And if we wish to, we could divide both sides by force, and we get an empty bracket, which means dimensionless. Okay, so therefore the answer to this problem, which is 1.8, is that the constant 3 pi is dimensionless. All right, so that's it for our first vodcast of Chapter 1, our second vodcast of the class. So if you go through and start the homework, you should be able to do the first 3 or 4 problems, and I'll be recording again very soon. So until then, have a great day.